Hi, I'm Andrew Freeman, a PhD student from the University of North Carolina at Chapel Hill, and I will be presenting our work in asynchronous representation for video triage. Now, to begin, let's kind of talk about what we mean by a video representation. So, traditionally, when we're talking about video, we are referring to a sequence of discrete image frames. So each frame is just an independent image, and then a video is just playing back a sequence of those images back to back. And this has kind of been shaped by ubiquitous imaging hardware. Every camera basically up to this point has captured video in this way, but we argue that we're no longer technologically limited to this sort of representation for video processing applications. So instead, what we propose is to not just measure the intensity integrated over a fixed period of time, like a discrete image frame, but rather measure the amount of time taken to fill a given intensity. So we kind of illustrate these two different models. On the left, you have kind of this traditional notion of what a video is. You have fixed length time exposures for each image. On the right, we instead measure how much time does it take for us to accumulate a given intensity. And we do this with this adder representation where each pixel we kind of track independently and asynchronously from one another. So we allow a pixel to integrate intensity until reaching a threshold 2 to the d. And once it reaches that threshold, we're going to output a piece of data, what we call an event, that expresses what that value is. This event is going to have the x and y coordinates, d, which is a decimation threshold, and delta t, how much time it took for it to accumulate that threshold. And then we'll reset that pixel's integration and start integrating again. And the cool thing about this idea is that each of these events directly expresses an intensity. So you can take 2 to the d over delta t and find out how much intensity was accumulated. And especially cool is the fact that d is dynamically configurable on a per pixel basis. So this what allows us to adjust the pixel sensitivities according to what is happening in the video. And that'll be more clear here in a second with an example. But basically this means that if you have a video and you transcode it to this adder representation, as we call it, then a stable pixel that isn't changing very much will have fewer events. They will output less frequently, and it's going to have a higher d value and higher delta t values than pixels which might be changing a lot. So where there's rapid motion in a scene, you will have more events, lower d and delta t. And we can kind of see this displayed here where we visualize these adder events. So this is taking a frame video, transcoding it to adder, and we can look at the different channels. So if we have these adder images where each channel is a different piece of the adder data, so the overall intensity, the decimation factor d, and the delta t, it kind of looks really wonky because it's not just displaying intensity like we typically do with an image representation. Over here we can look at the d value. So this kind of determines how sensitive is the pixel to change. And then here we see the delta t values. So where the pixels are really stable, we'll have brighter values here and here. And where things are changing, like where these people are moving and talking and stuff, then we will have darker values, or the appearance of darker values, as d and delta t are lower. And I know this kind of sounds a little bit abstract, but we're going to hopefully make it concrete here in a second. But we're really addressing the problem of video triage with this project. So our problem statement here is that intelligence analysts need to be able to search through a wide corpus of videos to find the things that they're looking for. And surveillance videos may be high frame rate and or exhibit fast camera motion. So for example, with this project, we were particularly looking at car dash cam videos. And third, objects should be detectable at a high rate, and analysts should be able to quickly scrub to the segment of the video they're interested in. So to be able to quickly find the parts of the video that contain the stuff that they're looking for. So then how can we use adder, this kind of newfangled video representation that's asynchronous, to improve video triage? So our idea is that if we first transcode regular frame videos to the adder representation, then we can encode information about the temporal stability of pixels into traditional image frames. So what this means is that it can help standard object detection frameworks, which typically only look at one image at a time. So they just look at one image, look for the objects in that image, and each image is processed independently. But we can improve that by helping it to better separate the foreground and the background and distinguish objects based on the rate of motion. So if we're encoding this decimation factor D and the delta T values, then the object detection framework can learn, if there's a high D and delta T, that's not moving as much as areas where there's a low D and delta T, by only looking at one frame. So you don't have to look at a whole bunch of frames, you don't have to have a complicated recurrent structure, which means that you can still do object detection at a high rate. And to kind of evaluate this idea, we trained 2 YOLO v5 models with the same parameters. So the first model was trained on just images that had the intensity component of the adder images, so 2 to the D over delta T. And then the second model was trained on images with the full adder data. So each pixel has the intensity, a D value, and a delta T value, where a D and delta T are together describing the temporal stability of that pixel. We use the BDD 100K driving dataset. So this dataset has 100,000 front-facing car dashcam videos, with 70,000 of them for training, 20,000 for validation, and 10,000 for testing. Although there was only one object detection frame that was labeled per video, so we had 70,000 training frames. And this is kind of a visualization of our results. This is with the adder data. Obviously, like I said, it looks kind of crazy because we're visualizing these D and delta T components as well. You can compare that to just looking at the intensity component here. And we note that we only use grayscale because with the adder data we have 3 channels. To push these object detection models beyond 3 channels is going to require some modifications that is going to be the subject of future work. So for our results, I'll just briefly describe that our full-on adder representation can outperform the intensity component alone by up to 4% for MAP50 and up to 2% for MAP95, which doesn't seem like much, but we really emphasize that this is just by changing what is the representation of the data that we are feeding to the object detection network. So we're just changing the values that we're encoding, adding additional features that describe the temporal stability of these pixels, so describing some notion of motion within a discrete image frame, and we see an immediate improvement, a small improvement, but an improvement nonetheless. And we also seem to have better performance than faster RCNN tested on this data set in 2015, and that test actually used the full-on color images, whereas we're only using the grayscale components of these images for our testing. Now on the software side, with our project, we delivered this adder codec, which is basically an open source tool with out-of-the-box executables for transcoding frame video to adder, visualizing adder data, so kind of having a video player to play it back, probing the adder metadata, reconstructing frame videos for visualization, all sorts of things like that. And this is really going to form kind of the groundwork software for a lot of future work in asynchronous video representations. And we also created a front-end web portal for kind of exploring our triage ideas with our representation. So on this portal, an analyst can upload a video and it will automatically be transcoded to adder and run the object detection on the back end. And then we encode the object labels in a custom representation, which we then can stream to the client, the front end, and overlay those over a video stream of the original video that was uploaded. And then we have different tools for analysts to filter by certain object categories, quickly scrub to the points in the video that they are looking for, and we can see a demo of that right here. So this is kind of the general layout of the client. Analysts can upload a video, and you can also search by the title of the video. We implemented a tagging system as well, so an analyst can add a tag or a series of tags to a video that kind of describe at a high level, like what is this video about, what does it contain, and then you can open a video, it will stream in, and it will overlay the bounding boxes. So these videos that we are showing are 60 frames per second, and again, these bounding boxes were generated from our adder-based object detection. So what I'm showing right now on the screen is that you can kind of filter based on certain categories, and then this graph on the bottom right shows the frequency of those categories within the video. So here I'm scrubbing to a point that doesn't have many vehicles, and then other points that might have more vehicles. Now, for future work, at this stage, like I said, we've only evaluated our ideas on grayscale image representations, and using full-on color adder representations are going to require us to actually make, kind of low-level changes to the object detection frameworks in order to have more featured channels. So in this case, it would be up to 9 channels. We're also going to evaluate our system on transcoded representations of event camera data. So these are very new cameras that are just kind of gaining prominence over the last couple of years that actually capture data asynchronously at the source. So these cameras have much higher dynamic range and high speed. They can capture data with microsecond granularity compared to 30 to 60 frames per second with a regular video camera. And we will also continue to add features to our front-end dashboard to improve the experience for analysts and hopefully make something that can really be useful for the intelligence community. And thank you.